This talk deals with some neurophysiology topics that are usually hard to grasp by first and second year medical students. This is the third session of a fourth-part series. The session intended outcomes are listed here. You do not need to read them. They will be covered during the course of this talk. This talk will be conducted in a question and answer format. The first question is: an action potential can be defined as the tracing recorded from the time the voltage increase departs from the membrane threshold to the time it returns to the membrane threshold. A, true; B, false. An action potential can be defined as a sudden, fast, transitory, and propagating change in resting membrane potential. Yet this definition needs clarification for two reasons. The first reason is that an action potential can be viewed from the perspective of other than membrane potential change, and the second reason is that the term action potential is also used to define segments of what we have just defined as an action potential. I will first consider the action potential from its multiple perspectives. An action potential can certainly be viewed from the perspective of voltage versus time as implied by the just listed definition, but also from the perspective of excitability versus time, from the perspective of voltage versus distance, and from the perspective of ion permeability versus time. So let's start by looking at the action potential from the voltage versus time perspective. Voltage versus time representation is the way action potentials are most often studied and the representation most often used to relate to all other action potential representations. It is in the voltage versus time representation that the terminology issue arises, as you soon will see. In this frame, I have represented voltage in the y-axis. Voltage is being measured in millivolts. In the x-axis, we will have time. Time is being measured in milliseconds. I will now add to this figure several important parameters, which I hope you recognize from previous talks. First, the nurse point for potassium, which, as you see, is in line with -90. Second, the resting membrane potential, which in this sample corresponds to -70 millivolts. And the third parameter I will indicate in this figure is membrane threshold, which in this example corresponds to -53 millivolts. In this frame, I have introduced a wave, which we will label action potential. The action potential is here defined as the voltage change that produces a waveform traced from the time the voltage increase departs from the membrane threshold, which is in most excitable cells coincides with the opening of voltage-gated sodium or calcium channels, to the time the tracing returns to threshold. Thus, the action potential has an upstroke produced by depolarization, to which we will refer to as the rising phase, and a downstroke produced by repolarization, to which we will refer to as the falling phase. In this frame, I have shaded red the action potential as we have defined it. Before the action potential corresponding to the area indicated by the arrow, following an adequate stimulus, the tracing departs from the resting membrane potential and rises until it reaches the membrane threshold potential. We will refer to this segment of the tracing as the pre-action potential. The shape of the pre-action potential segment depends on membrane factors. The membrane factors relate to temporal summation and spatial summation, and stimulus factors, which include intensity of the stimulus and frequency. After the action potential, we have a segment that for now we will refer to as the after action potential. So the answer to this question is A. Next question. The voltage first time action potential representation is labeled in similar fashion by all researchers. A true, B false. The purpose of this question is to let you know that you are not alone when it comes to being confused about action potential labeling. Even in those action potentials with relatively similar morphology, researchers have used different names to refer to similar segments of the voltage first time action potential representation. The voltage first time action potential representation in this frame is probably the most widely used, but certainly not the only one in use. This voltage first time action potential representation is very close to the one we have described, but notice that what we refer to as the pre-action potential is here referred to as hypopolarization. What we refer to as rising phase is here referred to as depolarization. The term overshoot points to the peak of the action potential. What we refer as the falling phase is here referred to as repolarization. And what we refer to as after action potential is here referred to as hyperpolarization. This new voltage versus time action potential representation, it's also very close to the ones we have described, but notice that what we refer to as the pre-action potential is here called foot or local potential. The term peak appears to be synonymous with overshoot. What we label after action potential is here labeled after potential, but appears to initiate not after the threshold is crossed, but after the resting membrane potential is crossed. This representation is much the same as the previous one. The only difference is that the segment we have previously labeled as after action potential is labeled here hyperpolarization and seems to start from the point the falling phase crosses the threshold. This new tracing is one of the earliest voltage versus time action potential representation. It distinguishes the peak from the overshoot. The term overshoot is used to indicate all the segments of the action potential above 0 millivolts. It distinguishes three elements during the segment we initially referred to as after action potential. The first element is labeled positive phase. Right after it is an element called negative after potential, followed by another element labeled positive after potential. The use of positive and negative to describe these elements is confusing but rational. It has its origin in the terminology used in electrophysiology. In electrophysiology, an upgoing wave is called negative, while a downgoing wave is called positive. Hence, using this terminology, it is implied that the pre-action potential here labeled food, the action potential here labeled rising phase, overshoot, and falling phase, which I have now shaded in magenta, is the negative phase of the action potential. The area shaded blue, the first downgoing wave, is in this action potential versus time representation considered the positive phase of the action potential. Hence, the after action potential segment in this representation starts at the onset of the negative after action potential. Thus only includes the part of the tracing in brackets in this frame. By far, the most confusing labeling that you will find is this one. In this representation, the segment between the threshold and the resting memory potential during the falling phase is referred to as the negative after potential. So the answer to this question is B. Next question. The term action potential complex is used in the literature to refer to the combination of pre-action potential, and after action potential. A true, B false. To me, it would make sense to use the term action potential complex to refer to all the voltages first time changes that take place during sudden, fast, transitory, and propagating change in the resting memory potential, and to restrict the term action potential to the rise and falling phase as shown here. But a search of the literature does not reveal that the term action potential complex is used. Hence, physiologists and the students are left with having to intuitively decide when the term action potential is used to define just the rise and fall phases of the action potential, and when it is used in a wider sense to globally refer to the pre-action potential, action potential, and after-action potential. It would also make sense for all scientists to use the same labeling system, but it is not so. So the answer to this question is false. Next question. If the threshold of a neuron is changed from -53 to -47, the stimulus required to trigger an action potential must be stronger. A true, B false. This is the same figure we use to explain voltage first time action potential representation. I will use several mental experiments to answer the above question. In the first experiment, the threshold of the membrane is -53. If an stimulus is given to raise the membrane potential 70 millivolts, that is from -70 millivolts to -53 millivolts, as shown here, this stimulus will produce a pre-action potential strong enough to trigger an action potential followed by an after-action potential, as represented in this frame. If now we conduct a second experiment in which the threshold is changed from -53 to -47, and we give an stimulus with the same intensity as we used in the first experiment, that is 17 millivolts, the membrane threshold is not reached, and there will be no action potential. The third experiment is conducted by giving a stimulus that produces a 23 millivolt increase in membrane potential. as indicated here. Notice that such a stimulus will reach membrane threshold and an action potential will occur. So the answer to this question is A. Next question. Extrinsic factors influence action potentials, amplitude, duration, and shape. A true, B false. The figure in this frame shows the changes in an action potential morphology brought about by changes in sodium content of the fluid bathing the giant axon of the squid. When the giant axon of the squid is bathed in pure seawater, the action potential looks very different than when the action potential occurs in an axon that is bathed in seawater diluted with 50% tap water. Hence, hyponatremia decreases the amplitude and delays the rise of action potentials. This new figure shows the effect of temperature on action potentials. Cold temperature increases the amplitude of the action potential, whereas warm temperature decreases it. So the answer to this question is true. Next question. Extrinsic factors being kept the same, action potentials have a standard amplitude, duration, and shape for specific cell types. A true, B false. In this figure, you can see the typical action potentials from different cells. Lower motor neurons' action potentials are of short duration. Those from striated muscles tend to be longer. Those from smooth muscles even longer, and those from the heart ventricular muscles much longer. It is interesting the variety of action potentials found in the heart. In this frame, you can see an schematization of the heart labeling four structures. The action potential configuration we have just indicated not only occurs in the ventricular myocyte but also in Purkinje's fibers. The sinus atrial node and the atrial ventricular node cells have different action potential voltage versus time configurations. The reason for this discrepancy will be addressed later in this talk. So the answer to this question is A. Next question. The excitability versus time action potential representation has the same configuration as the voltage versus time action potential representation. A true, B false. In the prior questions, we have considered the action potential taking into account voltage versus time and divided the voltage versus time representation into the pre-action potential, and after-action potential segments. We have also mentioned the inconsistent terminology used to label the different segments of the voltage versus time representation of the action potential. Now we will consider the action potential in relation to excitability versus time. In this frame, you can see a voltage versus time action potential representation, the potassium nurse point, the resting membrane potential, the membrane threshold, the zero voltage point, and above it, the overshoot. Here, we can see the pre-action potential, the rising phase, falling phase, and starting at the point the tracing crosses the membrane threshold, the after action potential phase with its multiple segments. I will now introduce the excitability versus time action potential representation. Here in the y-axis we are representing excitability running from 120% to 0%. When the membrane is at the resting membrane potential, it is considered that excitation is at 100%. When the membrane potential is at the level of the membrane threshold, the excitation is considered to be at 120%. I will now introduce the excitability versus time action potential representation. As you can see, it is represented by the green tracing. At any part of the tracing that is above the 100% demarcation, and stimulus weaker than the one producing an action potential when the membrane is at rest will trigger an action potential. This occurs in the pre-action potential period when the initial stimulus is not enough to reach threshold and a second stimulus is applied. At the end of the falling phase, once the voltage time tracing has crossed the threshold as pointed out by the arrow, and later also in the after action potential phase. Any part of the tracing below 100% excitability line implies one of two things. Either an stimulus in order to produce an action potential has to be stronger than the stimulus required to produce an action potential when the membrane is at rest, or no stimulus, regardless of intensity, will trigger an action potential. Periods of low excitability occur here, and here. So the answer to this question is B. Next question. There is only one absolute refractory period. A true, B false. In this frame, you can see the voltage versus time action potential representation above in yellow and below in green the excitation versus time action potential representation. Indicated by the arrow is the absolute refractory period, which I have highlighted by a red rectangle. As you can see, the red rectangle expands into the voltage versus time representation. I have done so to stress the relation between voltage versus time representation of the action potential and the excitability versus time representation of the action potential. The absolute refractory period corresponds to the time sodium voltage channels are open or inactive. Hence, no stimulus will trigger a new action potential. Next to the absolute refractory period, we find a refractory period usually referred to as the relative refractory period. During this period, sodium voltage gated channels are closed and not inactive, but membrane potential has not been recharged. The term recharge implies that the membrane potential has not gone below its threshold. During this period, a strong stimulus is able to reset the membrane recharge point and trigger an action potential. Next, we have another period that requires a stronger stimulus than the stimulus needed to trigger an action potential with the membrane at rest. This period probably results from overactive sodium-potassium pump. I will refer to it as the second relative refractory period. During this period, the sodium voltage-gated channels are closed, membrane potential has recharged, but the membrane potential is more negative than when the membrane potential is at the resting membrane potential level. The last relative refractory period I have now faintly shaded. This period, as you can see, shares the characteristic of the prior refractory period. Sodium voltage-gated channels are closed, membrane potential has recharged, membrane potential is more negative than during resting membrane potential. So the answer to this question is A. Next question. Supernormal periods refer to the period just following the relative refractory period of an action potential, when axon membrane shows increased excitability. A true, B false. So there are periods of the action potential during which only a strong stimulus above the one capable of triggering an action potential when the membrane is at rest produces a second action potential, or that even a strong stimulus, doesn't matter how strong it is, cannot trigger a second action potential. But there are also periods where the opposite is true. I will now talk to you about those periods. Periods during which a weaker stimulation than the one needed to trigger an action potential when the membrane is at rest trigger an action potential. The first of these periods occurred during the pre-action potential. As highlighted here, this period is not usually labeled as supernormal because the term supernormal is reserved for after-action potential segments. Yet it must be stressed that during the pre-action potential, a weaker stimulus than the one needed to trigger an action potential when the membrane potential is at rest is capable of triggering an action potential if it occurs after an equally weak initial stimulus. The reason the neuron is more responsive is because sodium voltage-gated channels are closed but not inactive. Membrane potential is charged, and the membrane potential is closer to threshold that is less negative than when the membrane potential is at rest. Another period when a weaker stimulus than the one required to trigger an action potential when the membrane is at rest can produce an action potential is also present at this point, just after the relative refractory period, when the voltage versus time action potential tracing crosses the threshold, but the tracing has yet not reached the resting membrane potential. This period is called supernormal period. Unlike the refractory periods, the supernormal period is not present in all neurons. During this period, sodium voltage-gated channels are closed but not inactive. Membrane potential has recharged, and the membrane potential is closer to threshold than during resting membrane potential. A third period when a weaker stimulus than the one required to trigger an action potential with the membrane at its resting membrane potential occurs after the second relative refractory period, which I have highlighted here. During this period, sodium voltage-gated channels are closed, membrane potential has recharged, and the membrane potential is closer to threshold than when the membrane potential is at rest. So the answer to this question is true. Next question. All authors represent the refractory period as corresponding to the same segment of the voltage versus time representation of the action potential. A true, B false. In this figure, the absolute refractory period starts with the tracing crossing the threshold and ends with the falling phase reaching the resting membrane potential. As you recall, in the previous representation, the absolute refractory period ended in the middle of the falling phase, when voltage-gated sodium channels close. And the relative refractory period starts with the tracing hitting the resting membrane potential and lasts as long as the after action potential. In this representation, you can see the absolute refractory period starting from the beginning of the pre-action potential segment. And the boundary between the absolute and refractory periods is somewhere above the membrane threshold. In this other representation, the absolute refractory period starts after the tracing crosses threshold. The relative refractory period starts prior to reaching threshold. In this other representation, the boundary between the absolute and relative refractory periods is at the point the tracing reaches the resting membrane potential. Again, as I explained to you when we went through the different labeling of the voltage versus time representation, the point of showing you different excitability versus time representation is for you to be aware that they exist and not to be surprised when you see them in different books. The one I consider most accurate is the one we presented initially, represented here. So the answer to this question is false, B. Next question. Capacitant current is not involved in non-myelinated axonal conduction. A true, B false. In the prior question, we considered the action potential from the point of view of excitability versus time. In this question, we will consider action potential from the voltage versus distance point of view. In this frame, you can see a single action potential represented as a voltage versus time tracing, but were we to give a second stimulus once the tracing is below the threshold and continue to record at the same site, we would see a second action potential arising immediately after the threshold is crossed during the supernormal period. Now, if we were to give a third stimulus, we would see a third action potential and so on. To explain voltage versus distance, we will now use the same y-axis values, but in the x-axis we will place distance, as represented here, going from proximal region of the axon to distal region of the axon. So, during the rising phase, the polarization of an axon segments occurs. Positive charged ions enter the cell, producing a positivity inside the cell and a negativity outside. The falling phase, indicating repolarization, will occur in the same patch of membrane, producing a shift of membrane polarity with positivity outside the membrane and negativity inside. Yet, simultaneous with the repolarization of the proximal segment, the polarization of the adjacent distal segment, represented by the rising phase of the action potential, is occurring. Repolarization leads to intraxonal positivity and extraxonal negativity. This pattern of progression will go on, leading to distal progression of the polarization zone as shown in these frames. This progression poses two questions. The first question is, what makes distal patch depolarize? Once depolarization occurs in an axon patch, the positive charges travel distally by electrotonic conduction. Positive charges also travel proximally, but as you recall, the proximal patch is in absolute refractory period, hence unresponsive to stimulation. The second question is, what raises membrane potential in the distal segment in order for the membrane potential to reach a level where voltage-gated cation channels open? In this frame, I have represented a patch of membrane distally and adjacent to the depolarized segment in yellow to indicate that this membrane is being depolarized. As the result of arriving positive charges, thus undergoing pre-action potential changes. The pre-action potential changes are the result of positive charges from the outer membrane surface being displaced by the repulsive force of the positive charges inside the membrane. This phenomenon, the deposition of positive charges at the inner side of the membrane and repulsion of charges from the outer surface of the membrane, creates a capacitor current that drives the membrane to threshold. So the answer to this question is false. Next question. In most neurons, voltage-gated sodium channels open before voltage-gated potassium channels following a suprathreshold stimulus. A true, B false. In the prior question, we considered the action potential from the voltage versus distance point of view. Now we will consider the action potential in relation to ion permeability versus time. We will create a graph using permeability in the y-axis. 1 represents the permeability of potassium when the membrane is at rest. Hence, 10 represents permeability 10 times bigger than the permeability of potassium when the membrane is at rest. And 0.1 represents a permeability 10 times smaller than the permeability of potassium when the membrane is at rest. I have now introduced time using milliseconds in the x-axis. I have now added a green dashed line to represent the membrane at rest. I have now added an orange dashed line to represent activation, specifically the point at which highest number of open voltage-gated channels are present. I have now represented the corresponding color match arrows on the side of the frame. At rest, the permeability of potassium is, by convention, 1 and remains so for about 0.3 milliseconds. At rest, sodium permeability is 0.04, the permeability of potassium at rest, but raises to about 20 times the permeability of potassium at rest, in this example, 0.3 milliseconds after supramaximal stimulus. Whereas the permeability of chloride remains the same. So, as indicated by the double-headed arrow, sodium voltage-gated channels open before voltage-gated potassium channels. So the answer to this question is true. Next question. the permeability of cardiac tissue during action potential is the same for all cells. A true, B false. I have already shown you this figure. In it, I label 4 structures and place by their side their corresponding voltage first time action potential representation. Structures that generate spontaneous activity such as the SA node and the AV node do so because they have different type of action potentials, as you can see here in this frame, than the myocytes and the Purkinje cells. The potentials produced by cells in structures that generate spontaneous action potential do so by a combination of calcium and potassium current, but most importantly, they have a special type of sodium channels that produce a special current that, because of being so different from all other currents produced by sodium voltage gated channels, is called phony current. The channel producing phony current open after calcium and potassium channels, as you can see in this frame. The phony current is produced by gradual inflow of sodium through special sodium channels. The importance of these channels is that these special sodium channels appear to be the channels involved in producing heart rate variations. Drugs with norepinephrine action accelerates heart rate, while drugs that promote parasympathetic action slow down heart rate by their actions on these channels. In this frame, I have isolated 2 ventricular myocyte action potentials. To briefly mention about the current producing them. As you can see, the rising phase is due to the entry of sodium. The rising phase is then sustained by calcium current, thus prolonging the action potential. Other channels involved in myocyte action potential are 2 types of potassium channels, represented here with their corresponding flow patterns. So the answer to this question is false. Next question. The action potential represented here is likely to arise from which of the following labeled areas? A, B, C, or D? Potentials generated in different regions of the neuron have different shapes, characteristics, and names. Potential generated by chemical transmission at the dendrites, soma, and axon terminals are called excitatory or inhibitory postsynaptic potentials. Most of them in the axonal terminal are inhibitory. In this frame, I have only represented those potentials occurring in dendrites. Notice the time scale. Excitatory and inhibitory postsynaptic potential have long duration. Potentials generated at the initial segment are different from potentials generated at the notoranvir. Here, you can see a potential generated at the initial segment. At the initial segment, the preaction potential has a hump. The shape of the preaction potential results from the gradual arrival of electrotonically transmitted charges to the initial segment and, to lesser degree, to the charging of the membrane by capacitance current. The source of gradual arrival of electrotonically transmitted charges is the summation of excitatory and inhibitory postsynaptic potentials generated in the dendrite and soma of the neurons. The charging of the initial segment membrane to threshold by capacitance current takes very little time once enough positive charges have arrived at the inner surface of the membrane. Potential generated at the notoranvir lack the little hump because the arrival of electrotonic transmitted charges at the patch of membrane in the notoranvir is simultaneous, and the charging of the node of ranvir membrane by capacitance currents is very fast. So the answer to this question is B. Next question. Dendrites produce action potentials. A true, B false. This frame shows an action potential traveling through two neurons. One of the receiving neurons has a thin axon and the other one has a thick axon. When the action potential arrives at the presynaptic region, an excitatory neurotransmitter is released. In the neuron with the thin axon, there will be an excitatory postsynaptic potential, and the same will happen in the neuron with the thick axon. The neuron with the thin axon, having a short length constant, will not generate an action potential, as shown here. The neuron with the thicker dendrite, thus having a longer length constant, will generate an action potential, as indicated here. This frame shows a figure representing a Purkinje cell being stimulated by a single neuron. The length constant of the dendrite being very thin is short. Hence, the excitatory action potential should dissipate and not produce an action potential at the initial segment. Yet it does. The question is why? The answer is simple. The dendrites in the Purkinje cells are able to produce action potentials that boost membrane depolarization. This is so because the density of calcium voltage-gated channels is increased in certain segments of the neuron, thus acting as a relay station for the creating of small, slow action potentials. So the answer to this question is true. Next question. An action potential triggered in the initial segment of a neuron is spread to all dendrites. A true, B false. Unlike in Purkinje neurons, it appears that in most neurons an excitatory postsynaptic potential fades with such rapidity that upon arrival to the neuron body, the excitatory postsynaptic potential is not capable of triggering an action potential. Even if an experimentally induced high amplitude potential is triggered in a distal dendrite, as represented here, this large potential, as it travels in the dendrite tree, fades, not arriving to the initial segment with enough charge to trigger an initial segment action potential. Yet, as you can see in this new figure, when an action potential is triggered at the initial segment, the action potential propagates to all dendrites as represented here. There are many theories as to how and why this is so, but not a widely accepted explanation. The prevailing thought is that the spread occurs by electrotonic current and that its purpose is to erase all past input to the neuron, allowing it to start a new cycle with no memory of previous stimuli. So the answer to this question is true. Next question. In the neuromuscular junction of an striated muscle, the amount of presynaptic acetylcholine release influences that of the action potential. A. Amplitude, B. Duration, C. Shape, D. Time of onset. I will try to answer this question using mind experiments. We will start by placing a surface electrode over a muscle fiber membrane close to the end plate as schematically represented here, as you can see by the arrow, and in a more realistic fashion here. This electrode will be used as reference. We will use one more electrode to pierce the membrane under the end plate and place the tip of the needle just under the membrane. This electrode will be used as recording electrode. The imaginary end plate membrane has a resting membrane potential of -90 and a threshold membrane of -70. Hence, in a normal circumstance, an increase of 20 millivolts from the resting potential will open voltage-gated channels. We will use this arrangement to monitor the membrane potential of the muscle fiber. We will measure the membrane end plate potential in fundamentally two situations. In the first situation, that we will label experiment 1, we start by injecting the end plate with tetrodotoxin, a toxin that specifically binds to voltage-gated sodium channels, thus preventing an action potential generation. Then we will inject different amount of acetylcholine. Acetylcholine is measured in quanta. A quanta of acetylcholine is the amount of acetylcholine that raises the end plate membrane 1 millivolt. In the second situation, which we will label experiment 2, we will only inject different amount of acetylcholine. Let's start with the first experiment. Here we will start building a graph by introducing the x-axis. The x-axis relates to time. The 0 corresponds to the time acetylcholine is injected at the end plate. The onset of acetylcholine activity at postsynaptic region is known to occur 0.5 milliseconds after acetylcholine is released. The peak of its action is also known to occur at about 0.8 milliseconds. I have now introduced the y-axis. The y-axis corresponds to the membrane potential in millivolts. -90 corresponds to the end plate resting membrane potential. The red broken line I have just introduced corresponds to 20 millivolts above the resting membrane potential. This line represents the threshold for the opening of voltage-gated sodium channels. Now, as we previously mentioned, tetrodotoxin is injected first, and then we will start the trials with different amount of acetylcholine. We are doing so to see what happens when different amounts of acetylcholines are injected once voltage-gated sodium channels are blocked. I will be writing the number of quanta injected under the heading just introduced. In the first trial, 15 quantas are injected. The potential generated by this amount of acetylcholine is indicated by the broken tan line. Since one quanta raises membrane potential by 1 millivolt, the membrane potential will go from -90 to -75 and stop there, and it will drop. In the second trial, 25 quanta are injected. The membrane potential will rise to -65 millivolt, going above the voltage-gated sodium channel threshold, but since they are blocked, we would be able to see the peak level produced by 25 quanta of acetylcholine acting upon acetylcholine receptor channels. And then the membrane potential will drop. In the third trial, 38 quantas are injected, thus achieving a peak membrane potential of -52 millivolts. The threshold for voltage-gated sodium channels will be achieved earlier than in the prior trial, as you can see by comparing the point of crossing of the third trial with that of the second trial. During the fourth trial, 58 acetylcholine quantas are released. And as you can see, pointed by the arrow, the threshold would be reached even earlier in this trial than in prior trials. Remember that so far we have done all the trials with voltage-gated sodium channels being blocked, so no muscle fiber end plate action potential has occurred. Now we will do experiment number 2. The graph will have the same parameters, but this time only acetylcholine will be injected. The membrane potential changes occurring due to acetylcholine injection will be represented by broken and continuous lines. The broken line for the part of the tracing occurring as the result of positive charges entering through the acetylcholine receptor channels. The continuous line represents on the way up the positive charges entering through the activated voltage-gated sodium channels, and on the way down the positive charges leaving the cell through the activated voltage-gated potassium channels. I have introduced in this figure a heading to indicate the time of onset of the action potential. During the first trial, the injection of 50 quanta will not produce an action potential. During the second trial, 25 quanta of acetylcholine were injected. In this case, the threshold was reached and voltage-gated sodium channels open, followed by the opening of potassium voltage-gated channels, producing the solid line that you see in this frame. The onset of the action potential was 0.7 milliseconds after the injection. During the third trial, 38 quantas were injected, producing an action potential with a time onset of, as indicated here, 0.6 milliseconds. In the fourth trial, when we injected 58 quanta, producing an action potential starting, as indicated here, 0.55 milliseconds after the release of acetylcholine. So the answer to this question is D. Thank you very much for your attention.